Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss FRESNEL'S assumptions and rectilinear propagation of light. Let's begin. In FRESNEL'S diffraction, the scientist FRESNEL takes some assumptions to achieve the diffraction pattern. According to FRESNEL'S diffraction, in such type of diffraction, the source is at a finite distance from the slit as well as the screen. What are the assumptions taken by FRESNEL regarding his diffraction pattern? According to him, a wavefront can be split up into large number of strips which are called as the FRESNEL strips. Basically, he used Huygens theory of wavefront as we take a plane wavefront let A, B, C, D be a plane wavefront, that is the direction of propagation of light. According to the assumptions by FRESNEL, that wavefront can be split off into large number of strips, and these strips are called FRESNEL strips. That is a wavefront, that is a plane wavefront which is divided into large number of strips. That strips are named as FRESNEL strips. And these strips, or which is basically known as the zones, FRESNEL strips or zones. Are very small area. The area is so small such that each point on that of wavefront acts as a fresh source of secondary waves in all directions. Here the strips, FRESNEL strips, are also known as the zones, and the area of these zones are very small. Therefore, each point, if we take the points on that of zones, act as the source of secondary waves, and that propagates in all directions. Next assumption, the secondary waves emit from each element of that wavefront is continuous. Each point act as a source of secondary wavefronts, and these wavefronts are travel in all directions, and these are continuous in nature. Next assumption, the resultant amplitude at any point is obtained by the superposition of all the secondary waves reaching from various FRESNEL strips or zones. If there is a point P here, so what be the resultant intensity due to that plane wavefront? That is basically calculated as the resultant intensity at point P is due to the superposition of all the secondary waves reaching from various Fresnel strips or zones. This is one Fresnel strip, that is another Fresnel strip, that one be the another Fresnel strips. So, the intensity due to each Fresnel strip at point P, by adding all the intensities, is nothing, that be the intensity at point P due to the entire plane wavefront. Okay. Next, the effect at any point due to particular Fresnel zone depend on. So, the effect of each Fresnel zone at point P depend upon three factors. One is the distance of the point from that of zone, the distance of the point from the zone, at which distance that Fresnel zone from that of observation point. If the distance increases, then what will be the intensity at point P due to that particular Fresnel strip, and so on. Again, the inclination of the point with reference to that of concerned zone. The inclination means that one is the inclination. These are the inclinations of particular zone to that of observation point. These are the inclinations. That inclination show what will be the intensity of that particular zone at point P. Next, area of the zone. Area of the zone, if I take that zone, so the area will be the dotted portion, the area enclosed in between the two consecutive zones is the area. That area is responsible what will be the intensity at point P due to that particular Fresnel strips or Fresnel zone. And the inclination of that point with reference to that of concerned zone is easily calculated by using a formula. That formula is 1 plus cos theta. Theta with the inclination when theta is equal to 0 degree. Look here, when theta is equal to 0 degree, theta is equal to 0 degree, we have maximum inclination at that particular point. But when theta is equal to, this is the maximum, when theta is equal to 90 degree or perpendicular way, when theta is equal to 90 degree, cos 90 0, we have the minimum. When theta is equal to 180 degree, so that expression will be 1 plus cos 180 degree, which is equal to 1 minus 1 is equal to 0. So, behind that zone plate, behind that particular plane wavefront, means if a point will be there, let Q be the point, so there will be no such propagation of light waves. From that of expression, it is clear that light wave is propagated in forward direction, not in the backward direction. Here the amplitude will be 0. Now, by using the assumptions of Fresnel, we can easily analyze the rectilinear propagation of light. Here we consider light from the source S is allowed to fall on a narrow slit AB, and the diffraction effects are observed on that of screen. At point O, according to the propagation of light, so here we observe the central bright fringe, that be the wave front, that xy, this is the wave front. Here this region, Q be the point, that region is the geometrical shadow. If we take light propagates at an angle theta, according to that particular formula 1 plus cos theta, the Fresnel's assumptions, the effect along any direction is proportional to that of 1 plus cos theta, which is known as the obliquity factor. So, the obliquity factor one plus cos theta. When theta is equal to 0 degree, the effect will be maximum. We have central right one. As cos 0 degree, we have cos 0 is equal to 1, and the resultant effect we achieve is central right fringe. But when theta is equal to 90 degree, here cos 90 will be 0. So, we have the minimum intensity. Similarly, when theta is equal to 180 degree, the resultant effect will be 0 cos 180. When theta is equal to 180 degree, we have obliquity factor is equal to 0. Hence, we conclude that the amplitude of the secondary wave along backward direction is 0, and so no ray of light can travel in backward direction. In backward direction, no ray of light is travelled. Since the amplitude of secondary wave along backward direction is 0, so there will be no ray of light can travel in backward direction. Thus, from that of particular scenario, Fresnel was able to explain diffraction by considering the secondary waves originating from various points of that of secondary wave front, originating from various points of secondary wave front. He observed that inside that of a geometrical shadow, here alternate dark and bright fringes are obtained. Why this happened here? Due to light bends at the edge of the slit AB. The bending of light at the sharp edge of the point AB. Due to that, in geometrical shadow we obtain alternate dark and bright fringe, which is known as the phenomenon of diffraction. So, we observe that the rectilinear propagation of light, is only approximate. The rectilinear propagation of light is only approximate, means light not absolutely propagate in straight line, it bends at the corner. What be the possible scenario? The bending of light, when we use a large obstacle, we can't observe such effect. We observe, but in our naked eye we can't see that kind of phenomenon. But when that obstacle is so small, or we can say it is a sharp edge, as the wavelength of light is comparable, then we observe that kind of alternate dark and bright fringes inside that of geometrical shadow, which is the phenomenon of light named as diffraction, and that is observed Fresnel's. According to him, the rectilinear propagation of light is only approximate, and the secondary wave waves undergo constructive and destructive interference, even in the geometrical shadow, region. Okay. So, with the help of this video lecture, you understand how In case of Fresnel's diffraction pattern, we observe he used an assumptions to clarify his diffraction pattern. So, the Fresnel's diffraction pattern basically based upon his assumptions named as Fresnel's assumptions. What is Fresnel's strips or zones? Next, rectilinear propagation of light means the rectilinear propagation of light is not absolute, that is approximate. Why that happened? Mathematically we show it. So, with this useful and informative notes, let me wind up this session. Thank you.